Hello everyone, my name is Efido and I'm here to present you our paper on benchmarking ground truth trajectories with robotic total stations. Benchmark stands as vital cornerstone in elevating SLAM algorithm within mobile robotics. Consequently, ensuring accurate and reproducible ground truth generation is vital for fair evaluation. A majority of outdoor ground truths are generated by GNSS, which can lead to disappearances over time. Recent research showed that robotic total station (RTS) setups are more precise and can alternatively be used to generate these ground truths. In our work, we try to compare RTS and GNSS systems, precision, and repeatability. We try to demonstrate that RTS setups give more reproducible results compared to GNSS setups, and that RTS can be used for benchmarking SLAM algorithms. To ensure accurate and reproducible results, our experiments follow a standardized protocol. RTS surveying instruments are prepared, aligned, and equipped with prisms to optimize visibility. Extrinsic calibration is performed to express all data in a common frame. After each deployment, a final extrinsic calibration is carried out in the laboratory to ensure data consistency. The obtained data is then processed using our pipeline, which employs various filtering techniques to enhance trajectory precision. We use a linear interpolation for unsynchronized RTS positions. At the same time, three GNSS antennas mounted on the prisms ensure precise RTK positioning, with a static antenna providing real-time corrections. As you can see, our setups here is represented with the three total station RTS that are following our clear path Robotic robot. On the robot there is three prisms and then three GNSS antennas mounted on top. In our work we use these two metrics. The one that is represented on the right is the interdistance matrix, which is used to evaluate the precision of each system and allows us to compare them. It is computed with the distance between each synchronous triplet of RTS target position or GNSS antenna position. The second one, which is represented on the left, is an inter-experiment matrix, which is used to quantify the difference in precision obtained between two experiments done at different times. Positions from separate experiments are considered close by calculating their nearest neighbor distance. As you can see, here is one of the experiments we conducted on the campus of Université Laval. This is the path followed by the clear path Robotic that we chose in our metrics and results. Our study demonstrates that RTS setups offer medium sub-centimeter precision at 6.8 mm, while GNSS setups provide medium precision around 1.3 cm. RTS setups exhibit consistent reproducibility with a medium margin of 8.6 mm, whereas GNSS systems have higher disparities at a medium level of 10.6 cm. Our graphs on the right showcase the gain of RTS in terms of precision and reproducibility compared to GNSS. However, on the left figure, we can see the line of sight limitations for the RTS setup due to the robot navigating on the campus in front of trees or a person, thus resulting in less measurement points for RTS than GNSS for ground truth trajectories generation. Through this work, we successfully integrated both RTS and GNSS ground truth acquisition systems. But there is some RTS limitations, like the line of sight dependency, the high cost associated with RTS, and the requirements for post-processing for data refinements. But it is a favorable trade-off, enhancing accuracy and reproducibility for ground truth trajectories despite RTS limitations, combining both RTS and GNSS, offering benefits. It shows that both RTS and GNSS setups are a valuable solution for improving SLAM benchmarking. Future work should explore the complementarity of both systems for 6DOF trajectory reconstruction. Thank you for watching. Don't hesitate to go on orlab.ulaval.ca to see our work.